Hi, this is Mrs. Basin, and today we're going to talk about acid-base reactions, which is section 4.3. So far, we've talked about precipitation reactions. So another type of what we before would have called a double replacement reaction is an acid-base reaction. So this is a special type of what we could classify as a double replacement reaction. So before we start, we need to talk a little bit about the definition of acids and bases. So an acid is something that increases the concentration of H plus when it's dissolved in water. There's two different definitions that we'll talk about. That first definition that we just said, that's called the Arrhenius definition. He was a scientist. That was his definition of an acid. Bronsted-Lowry were two other scientists that worked together, and they defined acids as proton donors. Now, we are going to talk a lot more about acids and bases later on, but for now, if we think of it as it's something that either increases that concentration of H plus or it donates a proton. There are 7 strong acids, and by definition, a strong acid completely dissociates in solution. So these are something that you do kind of have to memorize because this will help you decide whether or not, when you're doing net ionic equations, for example, whether or not those completely dissociate. These would also be classified as strong electrolytes, like we talked about in class today. Bases, definition of base, again, there's 2 definitions for this. Arrhenius' definition was it increases the concentration of OH minus when it's dissolved in water, and Bronsted-Lowry's definition is that bases are proton acceptors. And again, we'll get into a lot more detail with that later on, but for now, just so we need to be able to identify what an acid is and what a base is. Strong bases are the hydroxides of the alkali metals, so sodium hydroxide, potassium hydroxide, etc., and then the heavier alkaline earth metals, so calcium, strontium, barium hydroxides. And again, we need to know that because we need to know how to dissociate those. Like we said before, just to kind of tie this back into what we talked about today, the strong electrolytes are those soluble ionic compounds that we've already talked about. They are also the strong acids and the strong bases. So these strong electrolytes would be things that completely dissociate in solution. On the other hand, the weak electrolytes are weak acids and weak bases. And we saw that today with the acetic acid where it doesn't completely dissociate, so it doesn't conduct electricity as strongly as something like hydrochloric acid, which is a strong electrolyte or a strong acid. Okay, so let's just look through a little example here and classify these as strong or weak electrolytes. So my first one here, calcium chloride, that's an ionic compound, so that would be a strong electrolyte. So it would completely dissociate, you'd get a very bright light. HNO3 is a strong acid, so that would also be strong electrolyte, completely dissociate. C2H5OH, this is an alcohol. This is ethanol. This is a molecular compound that's not an acid, so this would not dissociate at all. This would be like the sucrose that we use today in class. So this would be a non-electrolyte. This wouldn't dissociate at all. Next one, HCHO2, this is actually formic acid. This is an organic acid. Again, one way to recognize these weaker acids, aside the ones that we already know, if it starts with an H and it's not water, then it's classified almost always as an acid. So this particular one is formic acid. That would make it a weak electrolyte because it's a weak acid. And then finally, KOH, potassium hydroxide, that's a strong base. So that would be a strong electrolyte. Okay, when we look at acid-base reactions, again, like we said, what's going on here is the acid is donating a proton to the base, so there's a transfer of protons here. These are also known as neutralization reactions. So a neutralization reaction is when you have a strong acid reacting with a strong base. So when this happens, when you have a strong acid and a strong base reacting, you always end up with the same net ionic equation. So if we kind of look through this, we've got HCl, which completely dissociates down here. NaOH completely dissociates. When those ions switch places, just like our double replacement reaction that we've done before, we get NaCl, and then this turns out to be HOH, which is the same as H2O. Okay, sodium chloride is an aqueous solution, so that dissociates. And then water, because it's a liquid, just like the solid did today in class when we were talking about this, the water does not dissociate and it stays together. So then if we look at our next step here, our Cl minuses are spectator ions, those cancel out, Na plus is spectator ions, so we end up with H plus, OH minus gives us H2O. So my net ionic for this reaction would be H plus OH minus gives me H2O. And this will be the net ionic equation for all strong acid, strong base reactions. No matter what the strong acid is or the strong base is, this will always end up as the same net ionic. The other type of reaction we want to look at are some gas-forming reactions. And this is another reaction that doesn't give us an expected product. So these are another form of a reaction that you have to memorize and you have to watch out for. So instead of giving you just the two products, the product decomposes and gives a gaseous product. So the two that we're going to talk about are acids and carbonates. So when you have an acid and a carbonate, you're going to get the salt of whatever that acid was, carbon dioxide, and water. And I'll do an example of each of these in a minute. The other gas-forming reaction is when you have an acid and a sulfide that produces salt and hydrogen sulfide gas. So what happens here, if we look at two examples, let's start with this first one, the acid and the carbonate. So let's say we have HCl and NaCO3, just sodium carbonate. So, and that would be Na2CO3. So what happens here is instead of just having those switch places, you get this carbon dioxide and water as a product. So we know we have CO2, we know we have H2O, and then the other product is going to be sodium chloride, NaCl. Another classic example of this, and we can talk more about this in class, is that volcano reaction that a lot of people do in grade school where you mix the acetic acid or the vinegar and the baking soda. Vinegar is an acid, baking soda is a carbonate, so you get those carbon dioxide bubbles, you get water, and you're also getting sodium acetate produced there. Okay, last example, acids and sulfides. So if I have, say, sodium sulfide, so Na2S, and HCl. What that gives me is the salt, so NaCl, and this one actually looks more like a double replacement reaction. The big thing here, so then I have this H and this S, is to remember not to dissociate the gas. So H2S, hydrogen sulfide, is actually a gas. So this would also stay together just like our liquid water did, just like our solids did. So this would not dissociate when we're doing those net ionics. The NaCl would, because that's our aqueous solution. So again, any acid, so in this case we used hydrochloric, but it could be any acid, reacting with any sulfide, you're going to get, the ions are going to switch, but you just have to remember this H2S is actually hydrogen sulfide gas.